Hello everybody, welcome to A to Z Learning Hub. Today we start sets, which is very important chapter in mathematics. You see, it is so fundamental chapter that it is interconnected with different chapters of mathematics like your relation and function, sequence and series, and indirectly it is also connected with calculus. So chapter you should learn this chapter very clearly and you will get more profit from this. You see, today our topic is set theory. You see, the word set was given by English mathematician George Cantor, and he is known as the father of set theory. Next come to what is a set? What is a set? You see, a set is defined as the collection of well-defined or distinct objects. What is set? Set is the collection of well-defined or distinct objects. What do you mean by well-defined or distinct? Suppose I will ask you, tell me vowels of English alphabet. Everybody will say these are A, E, I, O and U. Everybody. Next, tell me 5 natural numbers. First five natural numbers. Then these are 1, 2, 3, 4 and 5. These are well defined because everybody knows this number. Next, come to another point. Suppose anybody will ask you, tell me 3 best cricketers of India. 3 best cricketers of India. Suppose X will say, this is your Sachin Tendulkar, Rahul Dravid and Sourav Ganguly. Same question is asked to Y, then it will say, Y will say, that is your Sunil Gavaskar, Kapil Dev and MS Dhoni. You see, for first person, this is Sachin Tendulkar, Rahul Dravid and Sourav Ganguly. And for second person, it is Sunil Gavaskar, Kapil Dev and MS Dhoni. That means this question varies from person to person. That means the 3 best cricketers of India is not well defined because these 3 are best for X and these 3 are best for Y and like this. So the word best is not well defined. So we can say the 3 best cricketers of India cannot be set. But 5 vowels of English alphabet, it is a universal truth and it is true for everybody. So it is a set. So we can say set is the collection of well-defined or distinct objects. The word set is undefined. We say set is the collection of well-defined or distinct object, but in actual practice, if you see, the word set is undefined. Why it is undefined? You see, when we say set, what do you mean by set? Set means, another say it is the collection. What is collection? Collection means aggregation. What is aggregation? Aggregation means this is a class. What is a class? Class means set. That means set, collection, aggregation. Then a class set. These are in a circular manner. That means if we start from set and again we reach at set. So we cannot use a proper word in place of set. Therefore, we can say the word set is not well defined. We can say set, then one will say collection, one will say aggregation, one will say class, then it is the set. So as these are in a circular manner, that means it has no beginning point and it has no ending point. So we can say the word set is not well defined. You see another thing, you see, I am giving you some other examples of a set which are well defined, like this: set of 12 months of a year, set of population of India, all universities of India. All these are sets because these are well big defined. Shops, 12 months of a year, population of India, all universities of India, these are well defined. But I am giving you some other examples, you say these are not set. Like this, school, all shops, big of India. All big shops of India cannot be a set because we cannot define the word big. All good students of a school. All good students of a school. What is good? No one can define. Some students are good in reading. Some students are good in sports. Some students are good in singing. Some students are good in dancing, like this. So the word like big, small, great, beautiful, ugly, like this. What do you mean by element? Sentences containing these words cannot be the set. So because these words are not well defined. So I think you clearly understand which are sets and which are not set. Next come to your what is elements? Every member of a set, every member of a set is called its element. For example, suppose all vowels of English alphabet. You see these are A, E, I, O and U. So A is a member, A is an element, A is a member, E is a member, I, O, U, all these are elements because these are the members of a given set. These are called elements. You see, like set, the word element is also undefined. Why it is undefined? Somebody will ask you, what is the element? You say element means member. What do you mean by member? Member means object. What do you mean by object? Object means elements. These are also in a circular manner. So we can say the word element is also not well defined, but we consider it that every member of this set is called its element. So sets are represented by generally English capital letters like A, B, C, D, X, Y, Z. We also use the symbol like alpha, beta, gamma, like this, general representation. Again, the elements, general representation of elements are, generally you can say English small letter, that is the A, B, C, D, like this. You represent, generally you can also represent in other ways, but general representation, for general representation we use capital letters as the name of the sets and the small letters for the name of the elements. How can we say, how can you represent element, how elements are connected with set? Suppose you say A is an element of set A. We can write A belongs to A. Right? A belongs to A. You can say A belongs to A, or you can say A is an element of A. You can say A is in A, like this. A belongs. This symbol you use, A belongs to A. Suppose you say B is not an element of A. You write like this: B does not belong to A. This symbol does not belong to A. This is your A belongs to A and B does not belong to A, or B is not in A, or B is not an element of A, like this. This is your belong to and belongs to, and this is your does not belong to. Next come to your set representation. Set representation. Generally, sets are represented by two ways. One is, how can you represent the sets? Sets are represented by two ways. One is your roster form or tabular form. This is the old form. Another is set builder form or specification form. This is the modern representation. One is a roster form or a tabular form. This is the old form. Then next come to your set builder form or a specification form, or we can say this is the modern representation. In a roster form, you see, in a roster form, all the elements are written in a row, separated by commas, and surrounded by curly brackets. Suppose 12 months of a year. Somebody will ask you, write it in a roster form. How can you write? You write like this. This is the January, February, March, separated by commas. Then next come to your November, then December. You write in a row, separated by commas, give you curly brackets, and you name it. Suppose like A, B, or X, Y, Z, anything else. This is your roster form. In a roster form, all the elements are written in a row, separated by commas and surrounded by curly bracket, and you name it. This is the roster form. Next come to your set builder form. Set builder form or a specification form. What do you mean by set builder form or a specification form? In this form, you represent one element for or one symbol for all elements. You give one symbol for all elements, and you mention its defining property. How can you write? Suppose A is equal to January, February, March, November, December. Question will come, you write it in a set builder form. You write like this. This is your A is equal to X. For all members, you write X such that you get slash like this. X is a month of a year. This is the defining property. That means X is a month of a year means you will get your January, February, for every member you represent X. Or you can write it like this. A is equal to X, give these two dots. X is a month of a year. Question will come, suppose question will come in a roster form, you convert it into set builder form and vice versa. Question will come in your set builder form, you write it in roster form. Again, I am giving you another example also. Suppose it is given X is equal to, this is your January, March, May, July, August, October, December. How can you write it? You think it. This is a logic. X is equal to X such that X is a month of a year having 31 days. X is a month of a year having what? 31 days. Again, you see another example. Suppose P is a set. This is your January, February, May, July. How can we write it? Very important question also. How can we write it? P is equal to, how can we write? January, February, May and July. You write like this. X such that X is a month of a year ending with letter Y. You see, all these are January, Y, February, May and July. So, the question will come in a roster form. We write it in set builder form. There are again question also given in set builder form. You convert it into roster form. Next come to your, there are some sets which are given, they have a no defining property, but question will come, write it in set builder form or specification form. Suppose M is a set, this is your January, 5, class, pen, like this. How can I write? How can you write? January, this is a month, 5 is a number, this is a collection and this is a pen, instrument. How can you write? You write like this. Suppose it is given in a roster form. You write in set builder form like this. M is equal to X such that X is equal to January, X is equal to 5, X is equal to class, X is equal to pen. Just like this. Very important question. So, you can write this set. Suppose it has no proper defining property. You can write like this. Suppose you represent for all members that is X. You can write X is equal to January, X is equal to 5, X is equal to class and X is equal to pen, because they have no defining property. Understood or not? So, you try to understand. Next come to your question will come, very tricky question. What is the difference between set and a collection? What is the difference between set and a collection? You see, every set is a collection. Every set is a collection. But all collections are not set. Those collections which are well defined or distinct, these are sets. First, again I am repeating it. Every set is a collection, it is true. But all collections are not set. Cardinality of the sets. Those collections which are well defined or distinct, these are sets. Next come to. Here, I have already told you roster form and a set builder form. Cardinality or order of the set. You see, the number of elements in a set is called its order or cardinality. The number of elements in a set is called its order or cardinality. Suppose A is a set 1, 2, 3, like this. How many elements are there? There are 3 elements, 1, 2, 3. So you can say order of A is equal to 3, or you can write order of A is equal to 3, or you can write also the order of A is equal to 3, or you can write card of A is equal to 3. Like this, the number of elements in a set is called its order or cardinality. You see, the cardinality or order of the set is always greater or equal to 0. It minimum case it is 0. Under what condition it is 0, I will tell you later. And it is always greater than 0. and it cannot be a fraction, and it cannot be negative. Order cannot be negative, and it cannot be fraction, and it is always a whole number up to 0 up to infinity. In some cases minimum value is 0 and a maximum value is infinity. So this is called cardinality, and this number, this suppose order of A is equal to 3, 3 is called its cardinal number. So you remember cardinality of a set is always greater than or equal to greater or equal to 0, and it cannot be negative or fraction. Next come to your what are equal sets. Equal sets. Two sets are said to be equal if both have same element. Two sets are said to be equal if both have same element. Suppose A is a set that is the 2 and a 3, and B is a set x such that x square minus 5x plus 6 is equal to 0. Question will come, are these two sets are equal or not? Suppose you say A is equal to 2, 3, that means this set contains 2 and a 3. Next come to your B. You solve this question. X such that x square minus 2x minus 3x plus 6 is equal to 0, or x such that x into x minus 2 minus 3 into x minus 2. Middle term splitting. Minus 5x, I split it as minus 2x minus 3x. You split the middle term in such a manner that when you add these two terms, you will get minus 5x, and when multiply these two terms, you will get 6 into x square, that is equal to 6x square. That is minus 2x into minus 3x is equal to 6x square, but minus 2x plus minus 3x is equal to minus 5x. So that is equal to x minus 3 into x minus 2 is equal to 0, or we can say x such that x is equal to 3 and x is equal to 2, or b is equal to 2, 3. So we say these two sets A and B are two equal sets because they have same elements. It has A has 2, 3 and B has 2, 3. B contains 2, 3, but indirectly it is given in equation that is like this: x square minus 5x plus 6. We can say A and B are equal. Two sets are said to be equal if both have same elements. That means it has 2, 3 and it has 2, 3. Next, I am giving another elements also of equal sets. Suppose x is equal to 1, 2, 3 and 4, and y is equal to 2 to the power 0, 2 to the power 1, 2 to the power 2 minus 1, 2 to the power 2. You see, 2 to the power 0 is equal to 1, 2 to the power 1 is equal to 2, 2 to the power 2 minus 1, 2 to the power 2 is 4 minus 1, that is your 3, and 2 to the power 2 is 4. So set x has 4 elements, that is 1, 2, 3, 4, and y has also 4 elements, 1, 2, 3, 4. So these two sets are said to be equals. There are some axioms about equal sets. You remember one thing. What are these axioms? Repetition of elements in sets does not alter a set. Suppose A is a set 1, 2, 3, and B is a set, you write like this: 1, 1, 2, 2, 2, 3, 3, 3, 3. You see? So here 1, 2, 3, here 1 is repeated 2 times, 2 is repeated 3 times, and 3 is repeated 4 times. In this case, we will say A is equal to also B. Here A is equal to also B. Repetition. If 1 is repeated twice, it is considered as 1. Here it is also considered as 1, only 1, 2, and it is considered as 1, 3. Next, another important postulate is the change of order of elements does not alter a set. Suppose we can say A is equal to 1, 2, 3 and B is equal to 3, 1, 2. Here order are changed. Here 1, 2, 3. This is your 3, 1, 2. Here we can also say A is equal to B. Change of order of elements does not alter a sets. Next come to your different types of sets. First you see different types of set. First you see. First one is your null set. Null set or empty sets. It has different names. You can say null set, you can say empty sets, we can say void set, we can say universal symbol, that is your phi set. Phi set, Greek letter phi. What is null set? The set which has no elements. This set has a no element is called a null set. Like this, phi is equal to x such that x is both even and odd. It is quite impossible things. X is both even and odd. Because there is no number which is at a time which is both even and at a time which is both odd. So this is your null set. Another is phi is equal to x such that x is a month of a year having 32 days. It is also quite impossible. So you can say order of phi, by you can say order of phi is equal to 0. That means it has no elements. So these are called null sets. In set builder form, null set is represented like this. Phi is equal to x such that x is not equal to x. This is the set builder representation of a null set. Question will come, write the null set in set builder form. We can write phi is equal to x such that x is not equal to x, because we know everything is equal to itself. So here we say x is not equal to x means we say this is a null set. This is the set builder representation of a null set, that the x is not equal to x. This is the null set. Next come to your singleton set. What do you mean by singleton set? The set which has only one element, that means its cardinality is 1, is called a singleton set. Like this. Suppose A is equal to x such that x is both even and prime. X is both even and prime. That is A is equal to, there is only one number which is both even and prime, that is your 2. That means your order of A, or you can say order of A is equal to 1. This is a singleton set. You can also give an example like x is equal to, so that man. Suppose you write like this. It is one element, that is the man. So it is also a singleton set. The set which has only one element is called a singleton set. Similarly, if it has two elements, this is called doubleton, like this. Doubleton set. So singleton set means the set which has only one element, then it is called a singleton set. Next come to your another set. There are finite and infinite sets. Which are finite and infinite sets? The set which has finite number of elements. That means we can count the number of elements of this set. These are called finite sets. Like this, A is equal to x such that x is a month of a year. This is your finite set because its number is what? 12. Similarly, B is equal to x such that x is a population of India. X is a man of India or people of India. You can count the number of people of India. There is more than 140 crores. These are what? Finite sets, because we can count the number of elements of the sets. There are so many examples. Another is P is equal to x such that x is a natural number less than 11. So P is equal to what? 1, 2 up to 10. These are natural numbers. These are countable. We can count the number of elements. Next come to your infinite sets. The set which has infinite number of elements, that means we cannot count the number of elements of the set. These are called what? Infinite sets. There are infinite sets. Suppose I am giving you example, X such that X is a star of universe. We cannot count it. X such that X is a sand particle in a sea beach. So these are infinite. Now I am giving you some infinite set in the related to number system. You see, n is equal to X such that X is a natural numbers. This is an infinite set because you cannot count the number of natural numbers. That is the, or n is equal to, you can write 1, 2, 3, 4, 5, you can dot dot dot, you give this symbol for all infinite sets. These are natural numbers. There is no smallest natural number is 1 and there is no largest natural number. If we say there is one largest, this is the largest natural number, you just add 1 to it, then it will be greater than this. So this is an infinite set. Next come to your whole number. Z is equal to X such that X is a whole number. I am giving you some examples for infinite sets. That means Z is equal to what? 0, just add 1 0, 0, 1, 2, 3, 4 like this. 0 is the smallest whole number and there is no largest whole number. Next come to your I. X such that X is an integer. You can write list like this. I is equal to like 0, 1, 2, 3 dot dot dot. This is the -1, -2, -3 like dot dot. That means there is no largest integer and there is no smallest integer. This is the set of integer. You can write like this. I plus, this is your 1, 2, 3, 4 like. This is the set of positive integers. I minus, this is your dot dot dot, that is from -3, -2, -1 like this. This is the set of negative integers. This is also an infinite set. I is the integers, I plus is the set of positive integers, these are infinite, and I minus is the set of negative integers. That means all whole numbers are included within the integers and all natural numbers are included within whole numbers. Next come to rational numbers. Rational numbers, which are rational numbers? X such that X is a rational numbers. Rational numbers. Which are rational numbers? The numbers which are expressed in the form of P by Q. The numbers which are expressed in the form of P by Q, these are called rational numbers. Which are P by Q? Like this, 1 by 2, 3 by 4, 5 by 8, like this. Your every integer is also rational number. 0, because you can write 0 by 1, 1 by 1, 2, this is 2 by 1, 100, this is the 100 by 1. So all integers are included in the set of a rational number. After that, there are like these numbers. These are what? These are also rational numbers. You see, all rational numbers, all terminating decimal numbers like 0.32, 1.57, these are terminating. Terminating means the number of digits are finite after decimal point. All these terminating decimal numbers are rational numbers. You remember, all terminating. Which are terminating decimal numbers? The decimal numbers, the number of a digit after decimal point are finite. Suppose you see 5, 7, there are 2 digits. So this is also a rational number. 0.32, it is also a rational number. And there are some rational numbers, there are decimal numbers like 1.333333 like that. That is, we can write 1.31. This is your recurring non-terminating decimal numbers. Recurring, that means these are repeated. Non-terminating, that means these are not ended. These are also rational numbers. You see, all integers are rational numbers. All fractions are also rational numbers. All terminating decimal numbers are rational numbers. All recurring non-terminating decimal numbers are also rational numbers. You can say 3.121212, these are repeated. These are also rational numbers. These are all the rational numbers. Rational numbers also, this is all these rational numbers are infinite. They cannot count the number of rational numbers. Similarly, q plus, all positive rational numbers, q minus, all negative rational numbers, all these are infinite sets. Rational numbers are 2 types, positive rational number and a negative rational number. You see, those numbers which are not rational, these are called irrational numbers. That means the numbers which cannot be expressed in the form of p by q, these are irrational numbers. X says that x is an irrational numbers. It includes all sorts. That means the sorts whose radical signs are not determined. Radicals are not determined. Suppose q dash is like this: root 2, minus root 2, root 3, minus root 3, but not root 4. Root 4 is 2. It is the rational. Then your cube root of 5, like this. All these are irrational numbers because we cannot determine their radicals. Similarly, q dash plus a positive irrational number, this is infinite. All positive irrational numbers are infinite and all negative irrational numbers. That means q dash plus and q dash minus, these are also infinite set because we cannot count. Next come to your real numbers. Real numbers, which are real numbers? All the set of all rational numbers and irrational numbers are called real numbers. The real number is what? X says that x is a real number. It includes both rational numbers and irrational numbers. These are called real numbers. It is also positive real numbers, it is also infinite, and a negative real numbers, it is also infinite. Next come to your imaginary numbers. The numbers which are not real, these are called imaginary numbers. The numbers which are not real, these are called imaginary numbers. Which are imaginary numbers? Suppose like your r dash, this is the imaginary number, radical of a negative real numbers, root over of minus 1, root over of minus 2, root over of minus 3, like this. These are the imaginary numbers. Your root over of minus 1 is symbolized as I. This symbol I, this is your what? Imaginary numbers. So it is also an infinite set. Set of a real number is an infinite set. Set of imaginary number is also an infinite set. I have forgotten something. You see, in case of irrational numbers, you give all recurring non-terminating decimal numbers are also imaginary number. Like this, 1.325817 dot. These are irrational numbers. You remember, all non-recurring, non-terminating. These are not non-terminating. all non-recurring, non-terminating decimal numbers are irrational number. For this, your root 2, root 3, root 5, root 7, these are irrational because these are non-recurring and non-terminating decimal number. You see 22/7, this is your rational number, but your pi, this is your pi, and another value is your e, pi. E is called base of natural logarithm, base of natural log, that is its value of e is lying between 2 and 3, and the value of e is equal to 2.71 dot 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 like this. This is also non-recurring, non-terminating decimal numbers. This is irrational number. But pi is also irrational number because pi is non-recurring and non-terminating decimal number. But 22/7 is a rational number. It is irrational number. Pi is irrational number, but 22/7 is irrational number. Next come to your, I have already told you about real number and imaginary number, and the set of all real numbers and imaginary number is known as the complex numbers. Complex numbers, real numbers and imaginary numbers, it include both real number and imaginary number. It is the biggest set, and it is also infinite set because real numbers are infinite, your imaginary numbers are also infinite, the set of a complex number is infinite. So biggest set is a complex number, then come to your real number and imaginary number, then come to your irrational number, then your irrational number, then your rational number, then your integers, whole number, and natural number. So from natural number to complex number, all these are what? Infinite sets. All these are infinite sets. Next come to your equivalent set or similar sets. Which are equivalent sets or similar sets? Two or more sets are said to be equivalent or similar if both have same number of elements. If both have same number of elements, but the number of elements may be same or may not. Like this, suppose A is a set, we write 1, 2, 3, and B is a set, we write alpha, beta and gamma. You see, here A and B are two sets, same number of elements. It has order of A is equal to order of B is equal to 3. So we can say the elements may be same or may not. We can say A is equivalent to B or A is similar to B. These are the what? Equivalent set. Next come to another thing. Two equal sets are always similar, but two similar sets may not be equal. Two equal sets are always similar, but two similar sets may not be equal. Next come to two infinite sets are always similar. Two infinite sets. Suppose A is a set, this is your 1, 2, 3, 4, 5 like this. And B is a set, this is your 3, 4, 8, 9 dot dot like this. You see, what is the order of this set? Infinity. This, what is the order of B? Set A, and what is the order of set B? This is infinite. So since both have a same order, the elements may be or may not, may be same or may not. So we can say these are infinite, these are similar sets. And their similarity is determined by 1-to-1 correspondence method. That means 1 corresponds to 2, 2 corresponds to 4, 3 corresponds to 8, 4 corresponds to 9, 5 corresponds to other element like this. So two infinite sets are always similar. You remember, any two infinite sets are given, these are always similar. So this is our first class of set. You try to understand this. If you don't understand, you can ask me question, and for a detail you see the description. And if you like my channel, please subscribe it, share it, so that I will be motivated to teach you more and more interesting thing. For this, goodbye to all. Thank you.